Welcome. So this is a short presentation that I call Hacking with Skynet, how AI has powered adversaries. My name is Gavin. I go by the pseudonym GT Klondike. This is what I publish all of my research under. I'm an independent security researcher and a senior security consultant specializing in offensive security and application security. I'm very passionate about both attack and defense, which is why I'm here. And with that passion, I run a project called NetSec Explained, which is a YouTube channel and blog where I try to explain intermediate and advanced level computer network security topics in an easy to understand way. Personally, I feel like there's too many beginner topics, and so I want to take that to the next level. So it was mentioned earlier today that I presented actually last February on machine learning and security. And so that one was titled Machine Learning for Security Analysts. The idea is to kind of bring what machine learning is and what machine learning isn't into the hands of everybody. So before we get started, three things that tend to get used interchangeably. We have AI, machine learning, and deep learning. And so for many people, it's not really fully understood what the difference is between them. So before I get started, I kind of want to go over what AI is and how it all fits together. So if you look at this as an onion, AI is this massive umbrella where a bunch of different artificial technology components or algorithms exist in. So we'll have things like expert systems or classical image recognition. Part of that AI is machine learning. Machine learning is a set of statistical processes that allow us to build inferences from data. And then an even smaller subset of that is deep learning, and this is specifically deep neural networks. And we'll typically see deep neural networks used with image recognition, image generation, and things that require recurrent patterns. So heartbeat monitor will use something like a recurrent neural network, and that's a form of deep learning network. So a little background information. So that kind of brings us to the burning question right now is how has AI empowered attackers? So we've already seen that AI and machine learning have been this massive boon in the defensive side of things where we have even about, I think it's over 25% of our detection systems are using some form of machine learning. Sorry, I'm trying to set a stopwatch just so that I make sure I respect everybody's time. But sometimes it's easy to forget that this is actually a two-way street, right? As we get better at defending our systems, attackers get better at getting over, under, around, or through them. And so they're starting to use AI technologies in order to empower their own abilities. So I have this talk broken down into two separate parts. So we're going to talk about offensive AI tools. So what kind of tools and proofs of concepts already exist, what's out there that adversaries can take advantage of and try to attack our systems in new and unique ways. Why would we even want these kinds of tools? So maybe you're on the red team or a purple team and you're thinking about incorporating some kind of machine learning tool into your process, or you want to see what's available to add into your process and help you move at a much faster pace. Capabilities and trends, what are we seeing now? What will we soon be able to see in the future? Where is this going, basically? And then adversarial machine learning. Adversarial machine learning is attacking the AI models themselves. So according to Mr. Eric Graham, apparently there's a boat that we need to take a look at. So adversarial machine learning is what are the threat models, what types of attacks exist, what types of attacks don't exist, and how do we defend those systems, as always. So I'm going to get started with AI tools. Why would we even want these? So machine learning allows us to operate at speed and scale of actual machines. So we can build decisions and train a machine to act on those decisions, which greatly empower our own capabilities. It allows us to explore the target attack surface in new and unique ways because the machine is learning how the application or how the protocol works instead of coming in with our own inherent biases. And then it will allow us to assist in automating through manual analysis, so things that we thought were very difficult. For example, image recognition. Image recognition we're now seeing in facial recognition, which is allowing us to identify and flag people based on pictures instead of eyewitness accounts, which we know are a little flawed. And then, of course, because all of this is brand new to the machine learning algorithms that we're training, we can see and uncover hidden blind spots in these tools and defensive tools and software. So to give you an idea of how realistic this is, or how realistic this is becoming, the CyberGrand challenge from 2016 was a massive undertaking by DARPA to challenge a plethora of teams to perform what is basically a watered-down version of a full hacking phase. So we have vulnerability discovery, exploitation, post-exploitation. In this case, they needed to actually find, exploit the systems, and then patch binaries, all automated. So you can see here in this picture, the servers themselves are air-gapped. There is no human interference. And this is a capture the flag competition ran by machines for machines. And then, of course, some data theft where they had to go collect the flag, identify that it is a flag, and submit that. So today, some of the proof of concept tools that already exist are we're kind of seeing in the wild a little bit, and they're empowering adversaries to really upscale their social engineering, their defensive detection and evasion, so they can have their malware automatically detect that it's in a system like a honeypot or a sandbox, and then try to escape out of that system without any other user interference. Evaluating data leaks, so things like password dumps. Now, adversaries are able to use statistical analysis to identify things such as, actually a really good example is a tool that unfortunately I'm not going to be able to cover, but it's called PassScan. We already have some ideas of how passwords are built. So if we have a policy of 8-character passwords, you have to have 3 of the 4 common complexity settings, so an uppercase character, lowercase character, a number, and a special character. We already know that 9 times out of 10, a user is going to pick their first character as an uppercase letter, their last character as a number, the last 2 characters as a symbol and a number. So with statistical analysis, we can actually identify and generate passwords and the likelihood of these passwords being in particular environments. Network exploitation, so we can automate network exploitation, or there's been some proof of concept tools that would go out and automate network exploitation. And then software exploitation, so automatic fuzzing, so you can fuzz binaries using genetic algorithms to identify what type of input is getting to what location within the binary, and then over a period of time during that training, it can identify what the input is required in order to get to a desired result or a crash. There's also fuzzing for network protocols. So I just learned about HTTP2 recently and some of the issues that have been going on in that with IIS and Nginx causing denial of service because of poorly implemented network protocols. And so machine learning will allow us to kind of pick some of these things up much faster than we've been able to in the past. So starting with social engineering, we have StyleGAN. StyleGAN is a generative adversarial network. And what that means is it creates elements. So in this case, this is a project by NVIDIA. And all of these faces that we see here are machine generated. These are not real people. These are absolutely synthetic. And just to kind of show that there's no tricks up my sleeve, I also have StyleGAN for cats. So machine-generated cats here on the bottom, and that one in the bottom left corner I'm particularly proud of because it's just really messed up. So you can see, even though some of these look realistic, you can see this cat here in the bottom right corner. The carpet has a decent amount of texture and detail and all of the cat hair, which is kind of really why I like the cat pictures. And then you can see kind of a similar theme going on with that bottom left picture, but it's off so much that you can tell it's not an actual cat. There's already ways and research going on to try and identify some of these synthetic systems. So if you look at the backgrounds of each of these faces, they're very blurry. And especially this guy over here on the left, you can look in the background, and it kind of looks like there's a fence behind him, but it's a little warped, it's kind of bent. And so some of that's a little bit of telltale signs of a synthetic human being versus an actual human being. You can see with this girl also here on the left, the background, it kind of looks like there's a forest or a tree line, but there's warping going on. And it's just part of that generation process. So why would we use this? Well, for social engineering campaigns, it's very common for people to create personas. You want to put a face to a name so that it looks like you're actually talking to a human being. And so what many people will do is actually go to probably Google Images, go to the 10th page, so it's not something very obvious, and grab a stock photo or a picture of somebody's profile off of LinkedIn, something of that nature, put that up on their website and say, hi, I'm John. Now, if you're into investigations, you can just grab that same picture, throw it up into reverse Google image search, and it'll pop up that, yeah, no, this is a stock photo. This is somebody completely fake. You've been beaten. So why borrow somebody's identity when we can just create a whole new person? We have John. We have John's cat. We can even build entire websites using machine learning. And that kind of brings me to my next series of algorithms. So we have GPT2 and Grover. So these two do very similar things. These are long-form content generation systems. So you can generate things like blog posts, realistic-looking blog posts, realistic-looking Twitter feeds, Twitter threads, Reddit comments. And so now not only do you have a face to a name, but you can actually, over the course of a few days, generate an entire blog with realistic-looking articles that will kind of catch Google's attention so that you get logged and thought to be legitimate. And of course, because all of these are machine-generated, you are the only source of truth. You're the only place that these exist. There's no plagiarism involved or anything like that that somebody can easily Google. And so you must be real. And that just kind of adds to that believability score. For this reason, there's been a lot of ethics around it. So GPT-2, the full GPT-2 model was not released until just a few months ago. There was a lot of ethical debate and a lot of ethical concern this last summer about what it would mean to fully release this model, just because it would make spreading fake news that much easier. And so we already know with the Russian meddling and the Twitter bots and all of those things that misinformation campaigns are alive and well and absolutely terrifying. So if you want to terrify your friends and neighbors, play around with some of these tools. This one's actually the scariest in my opinion. We have Lyrebird and Tron. And so what these two do is they are synthetic speech to text. They are trained on human voices, and you can use this to engage even further on a phishing campaign or a vishing campaign. You can generate a series of scripts and really up your game. Adversaries can use this for things like robo-dialing, or calling in saying, hey, this is Karen, I'm trying to reset my phone number. You recognize my voice, which some banks, some financial institutions will actually do a little bit of voice recognition. You recognize my voice, so I sound like Karen, therefore I must be Karen, or at least believably Karen, when in fact I'm a 32-year-old male with my voice. So I'm going to play you a couple clips just to kind of see what these are. These first two are from Lyrebird. This last one is from Tron. So this first one, I want you to kind of compare the similarities and differences between the original voice and the synthetic voice.
In another moment, down went Alice after it. Never once did she consider how in the world she was to get out again.
And then here's the synthetic voice.
My voice might be generated by a computer, but I think it sounds pretty human. I don't know exactly how they made it, but I'm really impressed.
So what did you guys think? Is this somewhat believable? It sounds...
That's creepy.
Yeah. Well, and imagine what you can do if you're in another country and you're able to emulate somebody's voice. So somebody in India or Indonesia doing those vishing campaigns where they're saying, hey, this is...
Deposited into the
Yeah.
emergency fund.
I need $250 in
Other
Google
issue
cards.
there is that sounds pretty good, high fidelity. When you throw that over a phone connection with low fidelity,
Absolutely,
Yeah.
absolutely.
The noise
Add some compression. Sounds like you just have a shoddy connection. Yeah. And then Tacotron. Tacotron is from Google, and there is a TensorFlow and a PyTorch release of this. Unfortunately, I wasn't able to get it working on my system, but I grabbed one of their audio clips just so that you can kind of see like how realistic this sounds. But yeah, Tacotron. So I'm going to play this clip, and it's going to read this text blurb off to the side. This is from their research, already pre-trained, pre-made. The special thing about Tacotron is it was trained on 5-second clips of audio. And so the idea is to focus on localization. So as she's speaking, I want you to listen to the breaths that she takes, and remember that this is completely synthetic.
Only the photographs on the mantelpiece really showed how much time had passed. 10 years ago, there had been lots of pictures of what looked like a large pink beach ball wearing different colored bonnets. But Dudley Dursley was no longer a baby, and now the photographs showed a large blonde boy riding his first bicycle. On a carousel at the fair playing a computer game with his father, being hugged and kissed by his mother.
So what do you guys think?
It's not Stephen Hawking.
Yeah. Yeah.
So, really
Text.
interesting implication here.
So how much training went into actually getting those pauses?
Um,
That, do you think?
So that was based off the localization.
That's hard to do.
That was based off of their approach to training.
Okay.
And there's actually a presentation by Google kind of talking about its voice assistant and how they had to add things like filler words like and in order to sound believable, because we have filler words like and we take breaths, we do commas. I'm like trying to emphasize the breaths right now.
Right.
But yeah, no, so this is all like active research by Google. Like I said, this is something you can download, play around with. I believe they trained it for 9 days. So, and it was off of millions of just 5-second clips or 10-second clips.
So it was a lot of data.
Oh yeah, absolutely, a lot of data in order to get there.
A couple thousand sound bites. And
Yeah.
trained on that.
And it kind of gives you an idea of like how media kind of takes the research and really puts their own little like the world is ending twist to it. You'll find a lot on Google if you try to research these exact products or projects. This is a machine learning model trained off of 5 seconds of audio. And it's like, yeah, like a million times
Right,
off of
exactly.
millions of
Yeah,
different
5
5-second
seconds,
clips
yeah.
of audio. So it's not something where you can take, you're talking to the CEO or you have a recording of the CEO doing an interview, you take that and you train the model off of that, and now you sound like the CEO of a company. That's not how that works. And the Lyrebird is actually kind of interesting. So they're doing a closed beta right now, but when they do their official public release, there is it's supposed to be a text-to-speech, so auto-transcription service, but if you are a malicious actor, you can actually use it for up to, I believe, 3 hours of text-to-speech for $0, or it's like $14 a month if you want to go beyond that. So these are products that are actually going to be easier for adversaries to get a hold of. And all of this isn't to scare you or anything like that. This is just to kind of show. I know I'm doing a really good job. No, this is just to kind of show AI and machine learning tend to be considered buzzwords in our industry. And so as soon as we hear it, it'd be like, yeah, all right, go talk to the blockchain people. We don't care. But these are things to pay attention to. Like these are emerging technologies and things that we're going to have to fight and combat tomorrow. This one I really like, Sandbox Detection. So a team of researchers over at Silent Break Security, what they were able to do is take a process list and treat that as data. Now, my talk last year on machine learning and security showed you how we use data, how we extract features out of that, and then apply algorithms to infer information out of that data. So in this case, they're using the process list. And so they were able to build a model that can identify whether or not the system was in a sandbox. And then, of course, they took this another step further and tried to identify which kind of sandbox are we in. Are we in FireEye? Are we in Cuckoo? And then based off of that, they could take it another step further and try to use common escape techniques targeted for that specific sandbox that they're located in. So imagine what kind of havoc can happen if modern day malware is being used with this kind of sandbox detection. It'll be a lot harder for us to dynamically analyze what the malware is doing, what it's calling out to, things of that nature. So in this case, they were looking at the user count and the process list. They gave it an average host score, and they just said, OK, anything beyond this line is sandbox, anything beyond this line is a normal system, and then we can continue our execution. This isn't an actual tool. This is a step-by-step guide. Honestly, check out the Silent Break security team to see exactly how they did it. And it's not as it's not as hard as it may sound. It's actually kind of interesting. Now we start moving into automated network exploitation. So Deep Exploit and Goithon, these are two tools that do very similar things. They were both released at Black Hat Arsenal 2018. I believe Goithon also had an update for Black Hat Arsenal 2019. But what they do is kind of take pipelines of network exploitation and automate the information that it's collecting. So really fancy way of saying, OK, you have 10 systems or 10 networks that you want to try and break into. What's the first thing you do? Scanning and enumeration. You run Nmap. OK, cool. Based off the results of Nmap, are they using a web service? Are they using FTP? Are they using Jenkins, Tomcat, anything of that nature? So for example, it's a web service. OK, let's run crawler on there to see what kind of language they're using, what kind of software they're using. Are they using IIS, Apache, Nginx? Are they using PHP? Are they using Java? Are there any frameworks on top of that? So Drupal, WordPress, things of that nature. And so as you're getting all this information, you're collecting information from these pipelines, it's moving it down the road, and you're kind of filtering it down into this funnel to say, OK, I know that you're running a Windows 7 box with Tomcat running a Jenkins server, for example. So I'm going to try exploits from Metasploit that target Windows 7, exploits that target Jenkins, Tomcat, and other random Java exploits that we can do. So Goithon's really simple. It does just that. It looks at the web stack primarily, whereas Deep Exploit tries to look at the network services themselves, and it kind of takes DB autopwn to a whole nother level. Deep Exploit is also able to scale more. So you can create clusters of Metasploit machines, and then instead of dealing with dozens at a time, you can now target hundreds of systems at a time and go from there. It's really fascinating stuff. And then Deathstar, this one's really cool. So the idea behind Deathstar is, can we automate getting domain admin? Sometimes people like to think of machine learning or AI as, oh, it's just a bunch of if statements. And so that's why I wanted to present this flowchart to show that it's a lot more than just a bunch of if statements. So it kind of starts off here at the top, and it says start. Do we already have domain admin? If yes, we're done. Cool. All right, we don't already have domain admin, but do we have domain admin creds in our system? If yes, we're done. Cool. If not, then we're going to spawn an agent. And the first thing the agent wants to figure out is, where are we in the network? What does our environment look like? Do we have domain controllers? What groups are we in? And so it kicks off these over here on the right. It does get net domain controller, get net group member, invoke user hunter. And these are off of PowerShell Empire 2.0, I believe. And so it gets the domain information, it gets the group information, it tries to see, OK, what other users are in this group? Kind of like Bloodhound, if anybody's ever used Bloodhound, trying to build an attack graph from here you are to you are part of this group, which is part of this group, which has these members, and one of these members is part of this group, which is part of this group, which has a member that's part of domain admin. So if you want to go from here to domain admin, you got to take this path. And so that's kind of the general idea here, except automated, moving at machine speed and scale. And eventually it kind of gets down all the way here to the bottom where it says, OK, I'm on a new system. Is this Windows 7? If yes, let's run Mimikatz. Can we enumerate the running processes? Yes, absolutely. Are there processes being ran as users that we don't already have in our database? If the answer to that is yes, we'll use PS inject and try and pivot over to another user. And it repeats the cycle. So this is kind of interesting for me, especially as somebody who is really interested in building some of these machine learning algorithms, because the first question is, oh, well, where do I start? Do I need a PhD? What does a machine learning algorithm look like? And the trick is that you want to automate a common process or a common pipeline. So you start with something like an Nmap scan. OK, I can take information off of that. And there's a web server. So let's run GoBuster. Let's see what services are on there or what web pages are accessible. And you just build down the line from there. So if building your own machine learning model or AI for hacking is of interest, that's where you start. So that's kind of the end of the offensive AI tools. I know it just dumped a bunch of exposition on you guys. Think of it more as a series of rules and heuristics that allow you to make decisions. So it's not the format, it's the process, the thought process behind it all, right? So eventually it does boil down to what looks like a bunch of if statements. True. But it's the framework. It's like saying from computer science, like a red-black tree, oh, that's just a data type, or that's just a heap structure. This is more of an abstraction. This is a larger process or a larger vision of what that looks like and what you're able to do with it. Because managing hundreds of thousands of if statements can turn into this, which is much simpler and much easier to work with. Real quick, just a soundbite that I kind of want to leave everybody with is the best AI tool is the one that works best for your team. You don't have to be the fastest. You just have to be faster than everybody else. And so that's...
Faster than the bear.
Yeah, exactly. And that's really the name of the game, is if you, like, I'm just going to pick on Fortinet, for example. If Fortinet has a machine learning product or an AI product that is able to do and outperform than any of the other competitors, and that's all they have to do. They don't have to go beyond that. They just have to stay in front of the second place guy.
Yep.
So that's just kind of the way that our industry works. But things are moving so fast that it's kind of hard to just stay there. So adversarial machine learning. Now, this is going to be a bit of a change. Adversarial machine learning is actually attacking the machine learning models themselves. So adversarial machine learning, there's really three ways, kind of four ways to attack a machine learning model. So the first one is model evasion. And so this is actually trying to send adversarial traffic or malicious attack traffic and flag it or get it flagged as legitimate, benign traffic, something that you can get, something that's actually allowed through. And this happens in the inference phase. So as the model is making a decision. Model poisoning is where you actually get the ability to poison the well. You get to give it training data that it learns off of, and it slowly moves that line of what is acceptable and what is not acceptable to the point that you now have this entire area to play with. And then data leakage. Data leakage, I really kind of combine two smaller topics. One is model theft. So say you make an IoT device that uses some sort of machine learning technology involved in it, and that is now your intellectual property. Well, if it's an IoT device, I can just grab that, reverse engineer it, and now it's my property, and I as a competitor can either use that exact same model or just train it slightly differently, submit that to a patent office, and now you did all the work, but I'm making money off of it. And of course, private and proprietary information. So we're training these machine learning models off of the data that we have, which is also intellectual property. And in some cases, the model can actually leak information. So overtrained models, and I'll show you a couple examples in a moment, but overtrained models can actually leak information that can then be stolen by competitors or adversaries in order to steal healthcare information, for example, or map data, or any other form of proprietary information. So when testing a model, we approach it the exact same way as software testing. So we have Whitebox testing. This is where the adversary knows everything about the model. We know what features it's looking at. We know what the underlying architecture looks like. Is it a random forest? Is it a deep learning algorithm? And then we go from there. Whereas Blackbox is a little different. Blackbox, we know nothing about the model. So in this case, we treat it like an oracle from cryptography. So if you've ever taken a cryptography class or anything of that nature, you have an oracle that you can ask it questions, it gives you an answer, and you can ask it as many questions as you want. As attackers, we can ask it very specific questions and judge the answers that it gives us to kind of get or infer an idea of how it's learning or what it was trained on. And then we can build what's known as a surrogate model based off of that data. So we can ask it questions, it gives us answers. We use the questions and answers to train our own model. And then we can perform attacks on that model because now it's essentially a white box attack. And then the thing with adversarial machine learning is this concept of attack transferability. So this is a registered phenomenon where attacks in the adversarial space of one model can affect the adversarial space of another model, regardless of the underlying architecture. So we can have a deep learning model here. Adversarial examples for that deep learning model can affect something that's using like a random forest or an SVM or any other form of machine learning algorithm. So let's take a quick look at the attack surface. How does a machine learning model work, and what can an attacker actually influence? So we start here with a physical object or an observed event. We take that observed event and then we turn it into something that's actually consumable. So in many cases, this is bytes. In the case of an image or a person's face, you would take a picture of it, and so now they're digitized. And then based off of the input features of that face, we give that to a machine learning model. Machine learning model gives us some output, and then we have it, we automate or make a decision off of that output. So a really simple example would be like a network intrusion detection system. So we have attack traffic. The attacker is generating that attack traffic. We can use something like a packet capture or TCP dump in order to digitize or capture what that attack traffic looks like. And then we can feed the metadata from that capture into the model. It spits out attack probability. And based on that attack probability, if it's past a certain threshold, we just block the traffic. So as attackers, we can influence the attack traffic. And in some cases, we'll see this in a moment, we can actually influence the training of the model itself so that we can label attack traffic as benign. And so those are really the two entry points that we have. Or we can just steal the model as a whole. So when it comes to model evasion, we have adversarial space. So we have the theoretical space, which is everything, but we can't possibly capture everything. So we capture as much as we can, or this like smaller training subset. And so from that training space, we take some of that training data and use it for testing. This is data that the model didn't learn on, but it's data that we have properly labeled so we can see how well the model performs. The adversarial space is kind of right there against that testing space. So things that weren't captured in the training data, but can cause some unintended effects. Some examples of this would be like defeating naive Bayesian spam filters. And it's not just naive Bayesian, it's really many of the early day spam filters. So in my presentation last year, Machine Learning for Security Analysts, we kind of walked through the process of building and training a machine learning model to detect spam. And this is actually that same exact spam message that we did kind of at the end of the presentation. Now what's interesting about spam is a lot of times it's represented as HTML, or basically a small website in our email. So we look at the keywords and we decide, okay, we're 99% confident that this is spam. What if we put in a comment, something that the user doesn't see, but the machine learning model does see? We can just copy the entire Wikipedia page article of a horse, put it in there, and now we just padded a bunch of good words onto the end of our email, and it just got past our spam filter. Now this is 99% sure that it's not spam. So this is a real world example. This is what spammers were able to do to get past spam filters. Another way to do it is to take a picture of the email and paste that in as your email body. And so now there's no keywords to look at, so it just goes ahead and forwards it.
As an image?
As an image, really? Yeah.
And it'll pass?
Well, the idea is to fool the human into doing something, but to fool the human into doing something, you need to get past the spam filter. So if you get the message to the human, they'll take whatever action it is you need.
And
easier with nets also is some people will just add spaces between everything and randomly until it can pass the filter. So things are spread out. So human-wise, you can see it's the message, but the machine is like, I don't know what that is.
Yeah, and there's many different tips and tricks. For one reason, or for one example, there's a reason why spam emails are horribly misspelt, because the bad words aren't actually in the dictionary for the spam filter, so it just goes ahead and passes it. To see a more severe example of this exact same type of attack, the researchers over at Skylight Cyber actually took the Cylance AI antivirus and were able to modify a bunch of well-known malicious files and get it to pass the Cylance antivirus. The way they did that was they treated it as a black box. They reverse engineered it and had an idea of how the weights and the scores were being done off of various syscalls and strings in the systems. And then they just found one that was actually really interesting. It came from a video game, and they just said, all right, let's just take 1,000 of those, bolt it onto the side of this malware, and then send it back through and see what it says. So we have things like CoinMiner, Emotet, Zeus. All of these, it just bolted on a bunch of strings to the end of these binaries. So they're effectively the same binary. They're still malware. They still operate. But you can see that it went from this negative 997 score to a positive 997 score simply because it got all the good points. Really interesting article. Highly recommend you guys check this out. It's called Cylance, I Kill You. And all of the references, I believe John's working on getting the slides up online. So all of the references for the tools that I have shown here, the tools that I didn't get a chance to get to, and any other further reading if you're interested in this sort of topic is going to be in there. So how do we defend against evasion attacks? There's a couple ways. So one, we work with the assumption that we're going to see adversarial samples. A model is done learning as soon as it's finished training. And so let's go ahead and give it the tools to identify what an adversarial example looks like. And so we just create some of our own, throw them into our training data, and let it learn from that. There's also this concept of defensive distillation. The idea is instead of taking sharp angled points, we kind of smooth that out with a compression algorithm. And so it's a little bit easier for us to read the data. It's a little bit more difficult for an attacker to influence the data simply because now instead of being able to move sharp points, they have to kind of move an entire curve. And then one of the more interesting ones to me personally is this idea of monotonic classification. So that spam email example, we can see here, as we're giving negative words, things that are lowering our score or believability score, it kind of dips below this line, this threshold. Then we start adding a whole bunch of good words to the end of it, and it just shoots right back up, and now it's no longer considered spam, it's considered a regular email. Monotonic classification means that it grows in one direction, and so it measures the badness of a thing. So in this case, it only measures the bad words or the bad features. And so we can see these are the same numbers, but only measuring the bad ones. So we can see that as soon as it crosses that threshold, it goes past that barrier. There's no way for it to go back down because we don't care about the good words. We just throw those out. So once we've identified that you're bad forever. Sorry, Jesus won't save you. Model poisoning. This goes to your poisoning the well. So model poisoning is really interesting. These operate almost exclusively on online learning systems. So things like network intrusion systems, network intrusion detection systems, they sit on your network probably for a few weeks or a few months. They kind of learn what the baseline of your network looks like. And then anything that deviates from that baseline once it's finished getting that initial training, it detects and it flags as being, hey, this is an anomaly or this may be malicious. This is something to look into. So as an adversary, what if I can just slightly or slowly poison that well and move that line of what is and isn't acceptable, and then I can start playing over here, and the intrusion detection system is looking for anything to cross this boundary. So what does this look like in real life? Microsoft Tay is my favorite example. If you guys aren't familiar with Tay, it was a Twitter bot from Microsoft that the idea was it learns from the interactions that it has with people. So naturally, 4chan got a hold of this and decided to see how much can it learn? How much can we influence this chatbot? It got shut down 16 hours later. And it has still not come back online. So in terms of ROI or cost from that kind of attack, you got to imagine how many data scientists were involved, how many software developers were involved, and how much time it took to actually build out this model that has now just been totally scrapped because of some punk kids. And yeah, if you are not familiar with Microsoft Tay, or Tay AI, I should say, it took about 16 hours before Tay was going from, hi, I'm Tay, like, come talk to me, to Hitler did nothing wrong, and a bunch of racial slurs. So
Which isn't funny, but it's messed up that it could learn that quickly.
it's funny that it can learn that,
Right.
which makes machine learning very scary. I highly recommend the People's Chatbot Tay AI by the Internet Historian on YouTube. Check that out. Very funny guy, very funny explanation of what actually happened. For a slightly more technical type of attack, we have something called Jacobian Map Saliency Attack, JMSA. And the idea here is that we take that digitized data and we just tweak it a little bit in such a way that the machine learning model kind of picks up on that little tweak as being part of the feature. So if we take this 70 kilometer per hour sign, put these little dots in there, and now we have what is digital representation with a little artifact. It's really not that big a deal from a human perspective. You still know it's 70 kilometers per hour. But we put that into a machine learning model. The machine learning model is trained on these adversarial samples, and then we have a picture of a 30 kilometer per hour sign. And we put those same pixels in that place. It kind of picks those up as features of being a 70 kilometer per hour sign. So now it thinks that 30 kilometer per hour is 70 kilometer per hour. And you can imagine what kind of havoc that can cause. So like I said, these happen almost exclusively on online learning systems. And most of these are theoretical attacks, but we have seen some of them in the wild beyond just Tay AI. And it's just things to be aware of, especially if you have a system that's learning from online data.
Are you going to cover the stickers? Little attention stickers?
Yep.
Okay, cool.
Yep. Every single time I'm out here, you're just like, what about this? What about this? Wait like 2 minutes. I know, right? I'm not complaining. I just find it hilarious. Yeah. So real quick, defenses. The idea behind defending these systems is to limit the impact that an adversary has on our models. So this usually means that we want to delay retraining time. To give you an idea of how often things get retrained, I believe Facebook retrains their spam filter every 1 to 3 days. Yeah, there's a lot of information going through Facebook. I think Gmail is very similar to that. Yeah, but the idea is to expand how long you wait between those training cycles, simply because if I'm an adversary and I just pump a whole bunch of adversarial samples in one short time frame, it'll pick that up and then it has now permanently influenced our model. But if we expand that over a longer period of time, it's much more difficult for an adversary to influence things. Very similar to like the 51% attack in Bitcoin. It's very difficult to pull that off. Not impossible. Likewise, analyzing longer periods of data. So you're training it at whatever, 1 to 3 days or however quickly, but you're looking at data from the last 6 months as opposed to data from the last like week, 2 weeks, things of that nature. And then minimize impact of adversarial training samples. So this idea kind of comes from adversarial training samples. Throw those in there because you know your model is going to have to be dealing with that. If it's not a robust model, it's not a good model. There's also a concept of chaos engineering or engineering chaos. And the idea behind that is you know there's going to be problems in production, so cause those problems in production and then build processes and policies around those. So Netflix, for example, is a huge proponent of chaos engineering where they will just go into the data center and just start unplugging servers. And the reason why is because they rely on that uptime to be so important that they just assume something's going to go down at some point. So how do we force everybody else to go with that assumption? Because if nothing's wrong, you're going to ignore it, right? But now if you have the CIO walking in, unplugging servers every 2 weeks, and you know that, you better make sure those damn servers stay up. So that's kind of the idea behind this, like preparing for the training, the adversarial samples to come through. And then the last one that I have here is data leakage. So data leakage, this is what happens when your model memorizes the data instead of learns from the data. So it's kind of like cheating on a test. This image down here at the bottom, you might have come across this, I think it was last year actually, articles, the media, was coming out with, oh, the Google AI actually cheated and memorized all these maps that Google was trying to train it on. And that's a really common problem in the machine learning space, which is called overfitting. It just means that it didn't, yeah, you're forcing the hand. And that's not what you want because it performs really badly on things that it hasn't seen before. But what's really interesting from a security standpoint is now that the model has memorized all of this data, as an adversary, you can start pulling this information out. So imagine how impactful this would be if it was healthcare data or Apple proprietary information, Netflix proprietary information. This is millions of dollars or people's lives that can now be pulled out of these machine learning models, but we did it because we just wanted to make the thing work instead of worry about the security of it all.
Classified military installation locations where things are purposefully ordered.
Classified military installations. Yeah, absolutely. I think there's China purposefully modifies Google Maps just so that it's slightly off. To kind of hide some of its things. I believe the US did something to hide or replace its military, some of its military installations. Yeah.
As long as everybody wears Fitbit, so, you know.
Yeah, actually, my favorite, I just saw this article today. It's this guy, he had like 99 smartphones in a wagon. He was just pulling it, and it got flagged as a traffic jam.
Berlin in front of Google Berlin headquarters.
Yeah, Berlin in front of Google Berlin headquarters, yeah. I mean, there's just so many points of data. It's difficult to really anticipate the kind of wacky stuff that people will come up with or people will do intentionally or unintentionally. Yeah, so defenses to prevent model theft. There's a concept called federated learning, where you encrypt the model itself so that it's not reversible, and people are forced to use the model as a black box system. And if they can, build a surrogate model off of that. And then, of course, just making sure that your model's robust and it's not memorizing information or private information is not able to leak out. And so there's tests for that. A good data scientist will be able to account for these things. Here's your favorite, adversarial stickers.
Those aren't the ones I'm talking about. Those are cool, though.
Yeah, so I wanted to show some people like new adversarial stickers. Adversarial stickers are actually not that interesting. They look cool. But they don't really do a whole lot in the adversarial machine learning space. And the reason why is because they don't adhere to that attack transferability that I was talking about earlier. So I can train a model, I can build adversarial stickers off of that model, but if you train a model, those stickers won't work just because the way that the stickers are made. So the stickers are made by kind of using that model as a oracle and saying, hey, I want you to change only pixels around my glasses in this area, and I want you to make me look like this person. And so based off of the features of what the model was picking up for the person here on the right, it modified those pixels in that area around his glasses on the left so that when he puts on those glasses, he looks like the person on the right. Now, if I wear those glasses or if you wear those glasses, this is not going to become the same person, or in some cases, it may not even pick up that that's not your real face. So it got a lot of hype. This image on the right is the paper that really kind of like picked up the adversarial stickers and brought that to people's attention. So it got a lot of hype, but as people were trying to repeat the research, they were having a lot of difficulty. And eventually it kind of came down to this conclusion of like, yeah, they kind of work, but not that well. It's a very brittle attack. a really good video for information and reference is actually Sven from Defcon AI Village 2018. And so he has a half-an-hour talk on adversarial stickers and why they're super cool to look at, but really not that interesting as far as adversarial systems. So to recap, AI allows adversaries to operate at speed and scale. What we see right now is just the very beginning of what AI is able to do in the machine learning, or in the adversarial space and offensive security. And I'm really interested to see what's going to happen in the next year, the next several years, as more and more research is coming out and more applications of these offensive security, offensive AI tools will be in place. And then we're already starting to see adversarial attacks against real-world models. And so if you're working at a company that is thinking about or is already building AI or machine learning systems, please try to be aware and kind of bring this attention to them, saying, hey, we need to make sure that our models are robust, that we can actually protect against evasion attacks and poisoning attacks, because we know somebody's going to try and attack our model. We just need to make sure that we account for that. And yeah, so this is my contact information. Thank you, everybody, for coming. Thanks for a lot of the input. I love these discussions. They're fantastic. And then I know John's going to be working on getting the slides up here. So I'm just going to move this real quick. Here's all the read further references in case you're interested in some of these tools and other places to take a look at. So those slides will be online. You don't need to take pictures of those.
Thank you,
But
guys.
yeah,
Good to have. That was awesome.
thank you.